All right, everyone. We're going to go over problem 65 in chapter 5. And this is a pretty tricky problem. There's a lot going on here, and I'm going to walk you through it, and I'm going to sort of explain how I hope you will have thought about it, and if you were able to get all or even part of the actual solution taken care of, that's great. Ideally, this is a problem that I think would be um, overly complicated for a test or a quiz for the regular physics class. AP students, you can expect to see something along these lines, most likely in a free response question on the exam. Um, but I think everybody should target being able to kind of think your way through this problem. Think about what you know, what you would need, and even if you can't find what you would need, how you would use that to move ahead in the problem if you were able to figure it out. So the main um, story in this problem is that we have somebody who is sledding down a hill, and the information that we have is that the hill is at a 25-degree angle. That there is a 3-meter drop from the top to the bottom of the hill, and somebody is going to sled down the hill, and then when they get to the bottom of the hill, they will slide horizontally, and eventually come to a stop. On the horizontal section of the hill, we're told that the coefficient of friction, which is going to be kinetic friction because the person is sliding, is 0.05. On the hill itself, we're told in the problem to ignore friction. And the question is, how far is this person going to go once they get to the bottom of the hill? And in general, one of the things that I see in physics is that people want to kind of start with this endpoint, right? Like how if your question is how far is it going to go, maybe you think, oh well, I'm looking for a position, and you might even think, well, I'm looking for a final position. So let's see, final position is initial position plus initial velocity times time plus 1/2 acceleration times time squared. So all I need to know is figure out all this stuff. But what you're going to realize pretty quickly is that you don't have a bunch of this stuff. You don't know how long this person is going to be moving either on or off the hill. You don't know what their acceleration is. And it starts to become really overwhelming if you start with the answer. If you start with, this is what I'm looking for, therefore I need this to find it, oh, good golly, I'm stuck. So, what I always recommend is instead of starting with the answer, start by applying a process. And we've been talking with forces about the idea that, well, we're going to draw a picture. So, I did that already. And then we're going to make free body diagrams. And we're going to use Newton's second law. So, let's do that instead. Let's start with Newton's second law and see where we get. And one of the really important things to realize is that we really have two separate scenarios here. One scenario, while the person is on the hill and there's a slanted slope and there's friction, there's no friction. And one scenario when the person is at the bottom of the hill and it's a horizontal slope and there is friction. So we'll break this up into two parts and we'll look at it separately. For the first part, this person is on a hill, so we'll draw a free body diagram, and there's going to be two forces acting on this person. One is the force of gravity, which is the weight of the person in the sled. It's pulling straight down toward the ground. And the other force is the normal force, which is perpendicular to our surface. Because the person is moving parallel to the surface, it makes sense to think about our reference axis as being parallel and perpendicular to the surface. So we'll say that up and away from the slope is positive, and down the slope parallel to the surface is positive. So that means our gravitational force is going to be broken up into two components to align with that reference axis. Gravity is a force. The magnitude of the gravitational force is the weight of an object. It's equal to the object's mass times g, the acceleration of an object in free fall. But we can think of it as being two separate forces. One force that is perpendicular to the surface. Oops, that's going to be mg times the cosine of our angle, and one force that is parallel to the surface, which is going to be mg times the sine of our angle. The sum of the forces in each dimension is going to equal mass times acceleration in that dimension. And this is the next step in our process, is to sum our forces together in both the x and y dimensions and set them equal to mass times acceleration. So in the x dimension, we have one force in our positive direction. That's mg times the sine of theta, and that's it. There's no other forces. So that's going to be equal to the object's mass times its acceleration. And if we divide both sides by m, we see the mass doesn't even matter. We know what g is, it's 10. We know what our angle is, it's 25. So we can actually find the acceleration of the person in the sled as they go down the hill. It's going to be equal to g times the sine of the angle of the hill. That might be useful. In the y dimension, we have one force in our positive direction, the normal force, and one force in the negative direction, which is mg times the cosine of theta. That's going to equal the object's mass times its acceleration perpendicular to the surface. Well, there is no acceleration perpendicular to this slope. The person on the sled is not accelerating up and away or down into the hill. They're only accelerating in our x dimension. So that's going to be equal to 0. Oops, that is not a 0, that's a theta. And that is just a weird pen. So that means we could potentially find the normal force of this object on the hill. It's going to be equal to mg times the cosine of theta. We don't know the mass, though. Actually, I think we do know. No, we don't know the mass. We don't know the mass of the person. We know g, and we know theta. So we can't find the normal force from here. But if we figure out something about the mass, maybe we could. I'm not sure that this is going to be all that helpful because there's no motion occurring perpendicular to the surface. So now let's look at our free body diagram for the second part of the problem, where we have this object, this person, moving horizontally. So now we have three forces. There is the force of gravity, which is again straight down. I'm not sure why that happened. Let's see, this will work better. Which is straight down, and the normal force, which is straight up. There is no force in the direction of this object's motion. The sled and the rider are going to be moving in my drawing to the right, but nothing is pushing them in that direction. They're moving to the right because they were moving when they got to the bottom of the ramp. There is a force opposite the direction of their motion, though, and that's the force of friction. So the force of friction acting on the sled and the rider is in the opposite direction of their motion. In this case, all of the motion and all of the forces are aligned with a standard reference frame where up is positive and to the right is positive. So it makes sense to think about our motion in that sense. And we don't need to break any forces into components because they're all already aligned with this reference axis. So again, if we think about the sum of the forces, oh my gosh. If we think about the sum of the forces in our x dimension, it should equal the mass times the acceleration of our object in the x dimension. If we think about the sum of the forces in the y dimension, it should equal mass times acceleration in the y dimension. we still only have one force. This time it's the force of friction. So the force of friction is going to be equal to the boy and the sled, the mass combined, times the acceleration in the x dimension. In the y dimension, we have two forces: the normal force in our positive direction, the weight of the sled and the person in our negative direction, and that is again going to equal 0. There is no acceleration perpendicularly relative to the ground. The boy and the sled are not accelerating up into the air or down into the ground. So again, we could find the normal force here, but we don't know the mass of the boy. So that's a little bit of a problem. But we do know that the normal force, if we were to have the mass of the person and the sled combined, the normal force would be equal to that mass times g, the acceleration of an object in free fall. That would be the magnitude of the upward force from the ground on the sled and the person. So gosh, we've got some stuff here, but we really don't have enough to answer the question, which is how far is this sled going to slide once it gets to the bottom of the hill? And this is where we are able to start thinking about some other information that we might be able to get that could help us solve the problem. So if we go back to the beginning and we think about what we know, one of the real key pieces of information that we have here is the acceleration. We know how quickly this sled and rider are going to accelerate as they move down the hill. We know that they're starting from rest. Maybe we could figure out how fast they go when they get to the bottom of the hill. We would use kinematics for that. So if we have a initial position of 0, a final position that's the bottom of the hill, we don't know where that is. We have an initial velocity of 0. We have a final velocity that we don't know. That's what we're trying to find. We have an acceleration that we do know. It's g times the sine of theta. And I haven't done the math yet. Well, I have done the math, but we haven't done the math collectively. But that's something we could figure out because we know the angle and we know g. And then we don't know the amount of time. If we could figure out the amount of time, we have an equation we could use in kinematics. If we could figure out the distance that it goes, we have the equation, an equation we could use in kinematics. We don't really have any way of figuring out the time, but we do have a way of figuring out the distance because we know that the slope of the hill is 25 degrees. The height of the hill is 3 meters, and there's a trig function that relates the angle, the hypotenuse, and the opposite side. The sine of an angle is equal to the opposite side divided by the hypotenuse. So that means the distance that this sled and rider are going to go are going to be equal to the height of the hill divided by the sine of the angle. That's 3 meters divided by the sine of 25. So we can find the distance traveled here. It's 3 meters divided by the sine of 25. And this I would not expect you all to necessarily be able to get. So this is one of those places where what I was hoping you would do is recognize, well, I know something about the hill. I know I could find how long it is, but I don't know how. But if I could find that, then I could use the kinematic solver to find how fast the person is going to be going at the bottom of the hill. And in fact, you can. The final position here ends up being about 7.1 meters, and the acceleration ends up being 4.14 meters per second squared. And I used 9.8 for g, so if you use 10 for g, you're going to get a slightly different number. And if you put that into the kinematic solver and choose that third equation, the v squared, vx squared equals v naught squared, vx naught squared, blah, 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 it eventually tells you that this final velocity at the bottom of the hill is 7.7 meters per second. So that's helpful. Now we know how fast this rider is going on the sled at the bottom of the hill. But what we want to know is how far are they going to go? Well, we can kind of think about this the same way. If we want to know something about how far they go, that's a kinematics problem. So if we say at the bottom of the hill, their initial position is 0, their final position is what we're trying to find, the initial velocity at the bottom of the hill, well, that's the final velocity at the bottom of the hill from the previous part of the problem. That's 7.7 meters per second. The final velocity is going to be 0, right? They'll come to a stop. The acceleration, we don't know. And the amount of time, we don't know. So this is a problem because we don't have enough information to find how far this person goes if we don't know the acceleration or the time. So what else do we have that we could work with? Well, we have one other equation that we haven't looked at yet, and that's the equation that involves friction. We know that in general, the force of friction is going to be equal to mu times the normal force. We know mu, it's 0.05. The normal force we don't know exactly, but we know it's going to be equal to mg. So that means our force of friction is going to be equal to mg. And we have an equation here that we got from Newton's second law that has the force of friction in it. So let's see what happens if we do a little bit of substitution. If I substitute mg for the force of friction, what I get is negative mg equals mass times acceleration. And sorry, this is not, I forgot a key component here. Hold tight. Force of friction is not mg. Force of friction is mu. Mu times, mu times mg. My bad. It's 4:15 in the morning. Cut me some slack. So that means that if we substitute this in for our force of friction, we get negative mu mg is equal to the mass times the acceleration. We don't know the mass, but it shows up on both sides. So if we divide both sides by m, we get that the acceleration of the sled and the rider is going to be equal to negative mu times g. We know mu, 0.05. We know g, we can call it 10. So that means we know the acceleration, negative mu mg, or if you do the math, that's negative 0.5 meters per second squared. Now we have enough information to put into the kinematic solver to solve for the final position, and it turns out that's about 60 meters. So again, with this problem, I would not expect that you all would be able to put all of this together. Some of you, I'm assuming, were able to, but most of you probably got stuck at one or more of the steps, and there's a lot of them. It's a two-part problem, and each part of the problem has multiple steps in it. So this is a lot. This is a big problem, and what I'm really hoping that you saw is that there are missing pieces that if you could get them, you would be able to solve it. So hopefully you saw, for example, that, well, if you knew, how fast it was going here, if you knew the speed and the acceleration at this point, you have enough information then to figure out how far it's going to go. And hopefully you saw in the first part of the problem that if you just knew how far this sled went, you could figure out how fast it was going at the bottom. So ideally you would have been able to say, well, I don't have this, but if I did, I could find this next step. This type of a problem, as I said, is not going to show up on a test or a quiz. Individually, each part of this would be fair game. If I were to tell you, for example, an object is sliding along a surface with a certain speed, the surface has a coefficient of friction of such and such. How far will it go? I would expect that you could solve a problem like that. And I would expect that you could solve a problem like the first part of this, where you're asked, for example, how fast is something going at the bottom of a hill, given information about the forces that are acting on it. And that's where your ability to follow a process is going to be really important. And in this case, there's two processes. The first involves Newton's second law to find forces and acceleration. The second involves using that acceleration in kinematics. For the rest of the period today, you're going to be looking at determining the magnitude of a force and the resulting mass of an object that is necessary to accelerate your motion carts, your dynamics carts, up the ramps that you have set up in the room. And this is going to probably take a couple of days to do, so you'll be working on this today, and then when I see you next week, we'll continue working on this. There's going to be multiple rounds, or there should be multiple rounds of data collection. You're going to need the force of friction that you found in class the other day. That's one of the forces acting on your cart. And your goal today is to at least take a crack at trying to figure out how you're going to set this up. Do some calculations to determine the mass of the object that you're going to use to ultimately provide the force that pulls your cart up the ramp.